All right, line A4, learning task 4. We're on to video C as we're working through all the mini calculations inside of here. We're going to take a look at example number 6 and example 7 and 8. We'll go through a couple of them at this point now. Example number 6 just gives us a set of two components and says, look, if I take these two components and I place them in series, so I got a 125 volt source, and if I go and take a inductor, which is going to be 150 millihenries, and I place it in series with a capacitor, that is going to go and be 50 microfarad. What is my net reactance? So my XL net. To do that, we need to go my X net that I'm going to go and have. To do that, we need to convert each of these into XL and into XC, respectively. We know that XL is equal to 2 pi FL, and we know that XC is equal to 1 over top of 2 pi FC, like that. So we'll just go and punch these into the calculator, we'll pull out those values, and then what we can do once we know what our XL value is going to go and be, we can then take our XL value and we can go and add it to our XC value. XL and XC, and then that'll get us our total X net. We'll start with our XL. 2 pi times 60 times 0.15, that's 150 millihenry, which gets me to a value of 56.55 ohms of XL. Ohms XL. If I take a look at my XC over here, it's going to be 50 microfarads, so we'll go and punch that in. Start with a bracket, 2 pi times my frequency of 60 times, now we're going to do 50 microfarads, so 0.000, that's my milli. Now we're going to move into our micros, 0.50. That would be 50 micros. If I take a look at that, you don't need that last zero, we just kind of put that in there just because. We'll bracket that one, and then we will go and re-invert this whole thing. It gives me a value out of this one here of 53.05 that I'm going to have out of it. So my XC is equal to 53.05 ohms XC. We got to be real careful that we're identifying these at this point because we do have a lot of calculations where we're going to be utilizing all of them at the same time. Okay, the last thing that we need to do now is we just need to go and add these ones together. What we'll do is we will add these things vectorially. We will take 56.55 at angle 90 plus 53.05 at angle negative 90, and then we end up at a value of 3.52. And what we want to do is we see that this 3.52, you see this I over here? That means that it is a Y value, and note that it's positive, therefore it would have to be in the same direction as my X. So there would be a lagging power factor that we would have out of here. 3.5 ohms X. So 3.5 ohms XL net is what we end up with for this circuit over here. Straightforward enough. From there, you could go and calculate your values of, your line current and anything else that you wanted to go and do. You could calculate VARs that each of these would go and have. You'd be able to go and counteract those, etc. We're not going to do all of those, though, because we're going to move on to another larger example that has got a bunch of these values, and we're actually going to go and take this example and we're going to tune it a couple of times, where we're going to go and grab values and we're going to go and make some adjustments to these things. We'll start with our base calculation. The base calculation is just going to be us finding everything that we know off of this circuit over here. And in order to go and do that, we're going to have to add in a whole pile of values of resistance, inductance, our XL, and capacitance, our XC. What we're going to do is we're going to, as quickly as possible, move directly to that angle, because once we get that thing at the proper angle, everything else from there just forms as being part of that angle. We're able to drop all those values themselves off of it. Let's start by finding our XL and our XC. XL is going to be 2 pi FL, so we are going to go and take my 2 times pi times 60, because we're given a 60 hertz, times my L value, which was 200 millihenries, or 0.2. And when I hit enter, I see that I'm going to go and have an XL that is going to be 75.39, so it rounds out to become 75.4. XL, 75.4 ohms, XL. My XC is going to be the next one that we need to do. So we're going to stick a bracket, 2 pi times 60 times my capacitance value, which is 60 microfarads, so 0.000, that's my milli, 0.60, that's my micro, and then I take the entire thing and I reinvert that. And when I do that, I come out to a grand total of 44.21 ohms XC. 44.21 ohms XC over here. Lovely. Now that we've got that, what we can do is we can add all of our resistance, our XL, and our XC together and find ourselves an X net. Let's go ahead and do that. We're going to punch these values in. We'll start with our resistance. That's going to go and be, I'm going to start by changing my mode. You'll note that I'm inside of my rectangular. We're going to go into our polar. So we're going to go 25 angle 0 because it's resistance, plus I'm going to go and take my XL over here, 75.4, and it's going to be an angle of positive 90. So 75.4 angle 90. Plus, then I'm going to go and add in my XC, 44.21, and this is going to be an angle negative 90. It's going to be in opposition. Angle negative 90. And once I do that, I come out to a grand total of absolute Z for this circuit. That's going to be 39.97 ohms, and it's going to be at an angle of 51.3. That we'll round to. So I'm going to put these values in because these are really, really going to be critical ones to us. They're this 51.3 degrees, theta, 51.3 degrees that I'm going to go and have. And then my total ohms are the total ohms of impedance that I'm going to go and have off of that one there. Sorry, for a second I just couldn't remember that thing there. But my total ohms of impedance is going to go and be 40 ohms. It's 39.97 that we calculated. We are going to go and round it to that 40 ohms just because when we do so, the rest of our calculations over here for current just make it a little bit clearer. All right, Z equals 40 ohm Z that we have. Lovely. Now that we have that, what we can do is we can go and figure out our power, and we can figure out the rest of our voltages that we are going to go and have off of these by building triangles for these. Let's start by building our VA that we are going to have, our total power that we are going to go and have for this circuit. Total power for the circuit is going to be VA is equal to 120 multiplied by 40, so we'll just go and take 120. That I have got, I is equal to E over R, so 120 divided by 40, I said multiplied by 40, gives me a total current of 3 amps that I'm going to have. If that's my line current going through everything, that 3 amps multiplied by my 120 volts is going to go and give me my VA. So we'll take 3 times 120 equals 360 VA. 360 VA, and we'll drop down that value of amps that we found over there as well. 3 amperes. Lovely. So we've got 120 volts over top of 40 ohms of impedance, which is creating 3 amps, and that 3 amps then creates 360 VA. From that 360 VA, we are then able to go and build out a power triangle that we are going to have. That power triangle is going to be our solved power triangle, which means that it's not going to be quite the same as our actual values of bars that we're going to see here. But what we're going to be building at this point is my net that I'm going to go and have inside of this circuit. Let's just draw a impedance triangle over here. And our impedance triangle looks like this, where I'm going to go and have my total impedance of 40. Then I'm going to go and have my R of 25. And then I'm going to go and have my net, which is going to be the difference between these two over here. If you were to subtract these, you'd come out to a difference that's going to be sitting around 31.2. 31.2 ohms XL. And that net is just going to be this value over here, my 75.4 minus my 44.21. Let's punch that in. 75.4 minus 44.21, which gets me to a value of 31.19 or 31.2. That's what we're getting as our net value off of there. The rest of my values are going to go and follow the same thing. My voltage value is going to be made up of source voltage, 120 volts, and it's going to be dropped over top of two sides that are going to be made up of net values. And then my last one that I'm going to go and have, if that's my impedance, is going to be my power, which is going to be 360 VA, 120 volts, that's ohms over there, just to identify these. 360 VA that we are going to be dropping across there, and we're going to go and have watts, and we are going to go and have VARs off of these. Let's find what our nets are going to be, and then we're going to come back into these and see what the individual values themselves are going to be. We've done this angle, 51.3. We know what our VA is over here, so we can punch that in. 360 angle 51.3 equals a value of 360. We're still inside of that R theta. We just stored it in memory by doing that. We convert to the XY. We see that we are going to go and have, for my watts, 225 watts. That's the X value that comes out first. And then my Y value is going to be 280 net VARs, or 281 net VARs. So 225 watts. And then my net, sorry, one more time, 281 VARs net. So I'm going to write this down over here now for my total source VARs net equals 281 VARs lagging that I'm going to go and have. We're going to come back to these values later on off of these triangles. We're going to take a look at a couple of other values that are going to be going up and going down, creating those. We're going to go back to this one over here, same angular degrees that we are going to go and have. 120 volts as being my source, so we can figure out what we're dropping across our components. 120 angle 51.3. Enter, and it's right away converting because I was already inside of that XY, so I put it in as a polar, but because I'm in XY, it's displaying as XY right away. 75 is going to be my X value. That's going to be the number of volts that I'm going to go and see across my resistance. And then I'm going to go and have my Y value, which is going to be a positive 93.65. That's going to be my net amount of volts that I'm going to go and see across my inductance and capacitance together. 93.7. JRFM. Excellent. So we've got these as our net values. Are they actually these individual values? Well, if I were to take a voltmeter and drop that voltmeter onto my circuit, and if I were to go and draw from here to here, absolutely, I'm going to go and measure that 75 volts. That's going to be across there. But if I go across this inductor, like that, and like that, I'm going to be measuring greater than this 93.7 volts that I'm going to have because I've got a larger amount of voltage. What we're seeing inside of this triangle here is my net. Ultimately, usually that's what we're looking for is just, what's the net? What do we got left inside of that circuit? Because that's important to us. But when we're looking at our individual components, we want to see what the values themselves are going to be. For me to go and find that, my volts over top of there, I'm going to have to go and use my V is equal to my I times R. We got 3 amps times 75.4. 3 times 75.4. Which is going to get me to a value of 226 volts that I'm going to see across here. This seems insane, but it's not. 226 volts that I'm going to go and see across there. And if I take a look at my capacitor, I'm going to have to do the same thing. 3 times 44.21, right? V is equal to I times R. That's my resistance, my XC. I've got my current of 3 amps. It's going through this series circuit. So 3 times 44.21. Gets me out to a value of 132.63. So 100 and, we'll call it 133. Just for a rounded value over here, 133 volts that I'm going to go and have across there. If I were to go and measure across both of these at the same time, I'm going to go and see the net difference. And you got to remember that they've got opposite voltages values. If we place a voltmeter over top, it's an AC circuit, we don't see polarity, right? Voltmeters don't do that inside of AC. But when I place them over top of both of them, they're going to be in opposition. What we see over here is this 93.7 volts. That's what I would see right now. And the reason for that is because I've got a grand total of 226 volts that I'm going up there. It's a big, tall one there. But then I'm coming back down to that 226 by a factor of 133. Or not a factor, a voltage of 133. 226. So if I were to do this 226 minus 133, gets me out to a value of 93. We see that off of this one over here. This is a more accurate value. You know, we did a bit of rounding on this 226 and the 133, but that's showing us that we get this net amount that we are going to go and have over here. What we're also seeing is that we have got a voltage over here, 120 volts of a system, but my individual components in some cases can be higher or, you know, even up to double that they're showing these ones over here. They can go way greater than just double, by the way. This is one of the critical issues with a series resonant circuit. When we would get towards resonance, what we would continue to do is we would continue to go and drop the total Z, which would mean that it would get down to 25, which would mean that I'd have a lot more current going through here, which would mean I'd get a lot more voltage over top of each of those components. Okay, what do we have inside of here? For example number 7, they wanted to get the net reactance, which we did, 281 bars L. They wanted to get the total impedance, which we did, 40 ohms Z. They wanted to go and get the current, which we did, 3 amps. They wanted to get the voltage across each component. We've got this voltage, the voltage across our resistor is going to be 75 volts. We did it out of this triangle over here, but 3 times 25 would get us the same one there. They wanted to know the true power of the circuit. That's going to be the total watts. That's going to be this 225 watts that we are going to have. They wanted to know the VARs of my coil. We have not gotten to the VARs of the coil yet, but we'll do that in a second. They wanted to know the VARs of my inductor. We have not gotten to that yet. They do want to know our net VARs, which we had. We got the net VA, the apparent power, that's H. The circuit power factor, we don't have that, but we do have the circuit angles. Let's go and get the last ones here, which are going to be the VARs of both my coil and of my cap. VARs, we're going to just do I squared R. So I'm going to go 3 times 3 times 75.4. 3 times 3 is my amps over here. We'll just put that as 9. So 9 times 75.4. Gets me to a value of 679 VARs that I'm going to go and have. So VARs L. And then I'll do the same thing, 3 times 3, which is 9, multiplied by 44.21. Gets me out to a value of 398 VARs. 398 VARs C over here. What we're getting out of that VARs C there is a drop that is going to be applied against my VARs L. If I take a look at my VARs L are going to be going way up there, right? We're going to go see a rise of 679, but then we're seeing we're coming back down from that 679 by 398. And that's getting us our net over here. We'll do that, 679 minus 398. Gets me to a value of 281. 281 is going to be our net amount of VARs, and it's going to be a net lagging. Last thing we need to do is we need to go and find our power factor. Power factor is just going to be the cosine of that angle, so we're just going to go and take our cosine of 51.3, which gets me to a value of 62.5%. PF equals 62.5%, and we're going to go and write lagging because it's inductive, therefore it's called a lagging type of power factor. So that's our example number 7. They then have you go and draw voltage vectors for it. We did a voltage vector over here where we drew what we had for the final circuit, and we showed how these voltage vectors were against each other. They show that same thing where they're going up and dropping back down to go and show the amount. We see the 226, the 133, and then that we have the net of the 93 that's going to be across there. Then they draw it another way where they start by doing the resistance and then they go to the capacitive and come back up. Either one gets you to the exact same value that we are going to go and have. The next part to this thing is going to be, they ask us how our example number 7 is going to go and change if our inductor, which we're treating as being a resistance-less inductor inside here, also had an effective resistance of 10 ohms on there. And how is that going to go and change everything else? Well, let's go and take a look. We're going to erase a bunch of values over here. One sec before I do that. Yeah. Just give me a second. I'm just going to duplicate the slide here so we've got another copy of it that we can go and utilize. Because we have to come back to it for example number 9 as well. Or sorry, example number 10 as well. Okay, so we're on example number 8. How does this all go and change if the 0.2 Henry inductor also has an effective resistance of 10 ohms? Well, there's going to be a bunch of stuff that is going to be changed out on here. I'm going to erase a whole pile of stuff. We're going to go and keep a couple of things inside of here. First of all, what we need to see is, does my XL or my XC change? Well, what are they based upon? They're based upon the physical build, the L type, and the C type, as well as the frequency. Does adding in a bit more resistance change any of that? Absolutely not. It's not going to change any of that. So we are going to be able to leave our XL and our XC the same. If we've got that XL and XC that are going to be left the same, the only thing that we're going to be changing then would be our value of resistance, right? We're going to add in another 10 ohms of resistance. Now we had this as our original triangle over here that we had created. We are now going to go and add in a little bit of additional resistance, 10 ohms. Draw that in right over here. 10 ohms, that is going to be part of my coil over here. And how's that going to change everything? Well, we're just going to regraph everything that we had there before, right? We're still going to have the original 25 ohms at angle 0. Now we're going to go and add in an additional 10 at angle 0. Then we are going to go and add in our 75 at angle 90, 75.4 at angle 90, and then we're going to go and add in our 44.21 at, put that on the other side, 75.4, and we'll add in our 44.21 at angle negative 90. We're going to get to a net amount of resistance. I'll make sure I'm inside of polar mode. 25 angle 0 plus 10 angle 0, that's all my resistance is, plus 75.4 angle 90 plus 44.21 angle negative 90. Make sure that negative is in there. If you don't put the negative in, you're going to have some major problems with that. When I do that, it punches out a new value of impedance, which is going to be 46.88 or 46.9 that we can go and round that thing to. So we are going to see 46.9 for that one, my ohms impedance. That 46.9 is going to be that net that we see coming across here. So 46.9 that we are going to have for ohms Z. Let's find out what that angle is at, because that's also going to be critical to us. The angle is now dropped. Before, this thing was all the way up at 51.3. Now we are dropped down to 41.7. So angle becomes 41.7 over here. If my angle has gone down, what has that done to my power factor? Well, let's just take a quick look, right? Cosine of 41.7 means that I'm now seeing I'm going to go and have a power factor of 74.66, so 75% power factor. 75%, it's still an inductive circuit, so it's still going to be lagging that I'm going to go and have. But you'll note that this is better than what we had before, right? On our original one, we had 62.5 lagging, and we had an angle of 51.3. Now what we're seeing is we got 41.7, we got an angle of 75% lagging, so it's less lagging that we have over here. Lovely. That means that it's going to be better overall. We've got a better power factor out of here. Because we had this increase in the amount of resistance, our current is going to go down as well. Let's go and take our value of voltage, 120 volts, and we'll put it across 46.9. Gets me to a value of 2.56 amps that I'm going to go and have. Put that in, 2.56 amps. And if I've got 2.56 amps, I'm going to go and see different voltages that are going to be across each of these, right? This 25 ohms over here is going to be 25 times 2.56 equals a value of 64 volts that I will see across there. We see a drop in the value of voltage over top of here because some of that voltage is going across here. Now inside of your binder, it says VR becomes 89.6. They're actually talking about the total voltage that would be dropped across this resistance and the copper of this, but because we can't separate that, that's a dumb value. Just kind of ignore that one, cross it out, so that you don't go back to that thing later on trying to figure out what exactly is happening inside of there. My value of voltage for my capacitor is going to go and become, well, we're going to take 2.56 times 44.21. 113 volts that we are going to go and have. So we're dropping that value that we are going to have. My voltage across the inductor is going to be made up of the vector sum, right? We're going to have to find a Z for this coil now that this thing has an actual resistance and a reactance off there. So we're just going to go and add those two together. 10 angle 0 plus 75.4 angle 90, which tells me that this coil's got a total Z of 76.06. So 76.06 Z. We'll round that to 76.1. We'll find out our voltage across there. 76.1 times 2.56, which equals a value of 194.81. So across this entire inductor, the resistive and the inductive components, we're now going to go and see 194 volts that are going to be seen across it. If we compare these values that we have over here, we see that our value of volts across our inductor has dropped from 226. We dropped that thing down to 194. If we take a look at our capacitor, it had 133 volts over top of that. We've now got 113 volts across that. If we take a look at our resistor over here, it had 75 volts. We drew it over here, but it's 75 volts. Now we're dropping that thing down to 64 volts. So adding in a little bit more resistance has dropped the current, which has really served to go and drop a whole pile of our other components. We can figure out our net amount of watts, our net amount of bars and things like that at this point. We're not going to go and calculate the individual bars inside of here, but I do want to go and calculate my nets because we can do so off of that angle that we have over there. What's my VA? I don't know what my VA is, but we can calculate that. We'll go with 120 volts, my source voltage, times my source current, 2.56, which gets me to a total VA of 307.2. And I'm just going to go and punch that 307.2 in at an angle of 307.2 at an angle of 41.7, because that's what our circuit has changed to. 41.7, which gets me to a value of 307, once again because it's still inside of R theta. We're going to change it to an XY, gets me to a X value of, oh shoot, I've missed the second function over there. Should not be 9 over there. 1 second, let me just put the value back in, 307.2 at 41.7. second function, and now the number 9. I just missed that before, the second function. All right, 229 is going to become my x value. That's going to be my total amount of watts that I'm going to go and have now. So draw this triangle out here. 307.2, 229 watts that I'm going to go and have dissipated by this one. And if I want to know my net vars, it's going to become 204.35. 204.35 vars. What type of vars? Well, we see that we have got a primarily inductive circuit, so it's still going to be vars lagging that I'm going to go and have. Once again, when we compare these values over here, I see that my total VA has gone down. I see that my watts have gone up just a hair, and I see that my vars have gone from 281 down to 204. We've dropped the total number of vars because mostly we've dropped the amount of current that we are going to have inside of here. What we've really done is we have corrected our power factor. That's a really big deal to us, correcting power factor. The next question that they ask, moving on into example number 10, is they say, well, what would happen to that first circuit that we solved, example number 7, if we were to go and change our capacitance to a grand total of 30 ohms of XC? Well, let's go take a look. What happens when we change our capacitance to a value of 30 ohms XC? First off, we're going to have to go and remove a bunch of other stuff. Now, they don't say that we're changing any sort of frequency. They're just changing the capacitor to go and drop that. So we're going to have to go and lose all of those values, that. We're going to go and keep our 75.4. We're now going to go and make this a value of 30 ohms XC, and we're going to have to go and remove all the rest of these because we don't know exactly what is going to go and be happening inside of here. We need to redraw a bunch of triangles as well because all of our triangles are going to be screwed at this point because we've changed one of our circuit values inside of there. Well, let's start by creating our total impedance because we've got these values that we have over here and we've now just got to change value over here. So we're going to assign each of these their angle. This is going to be angle 0. This is going to be angle 90 because it's by inductive. This is going to be angle negative 90. And we'll add these all together. Polar mode there. All right. So we're going to take 25 angle 0. We're going to add that to my 75.4 angle 90. And then we're going to go and add that to my 30 angle negative 90, which works out to become a value of 51.8 as my total impedance that I'm going to go and have here. And it's going to be at 61.16 degrees. So we'll go back, write down those numbers, 51.83. 83 ohms Z. And we'll write down that angular value as well, 61.16. Roughly, it's going to be 61.2 degrees. So we'll put that into 61.2 now. Lovely. Now that we've got 61.2 degrees, we can go and graph out all the rest of our net amounts that we are going to go and have. We can figure out our net watts. Off of that, we can figure out a whole pile of other stuff. We'll start by developing our amps, though, because that's going to be the one thing that's going to be consistent inside of this circuit. We know how many volts we have for the circuit, 120 volts. We know what our total opposition is. The source doesn't have an eyeball, so it can't see what it's all attached to. So we're just going to go and apply our source value voltage over top of my impedance. 120 divided by 51.83. Gets me to a value of 2.31 amps that I'm going to go and have. .31 amps over here. So we see our current has dropped. Remember on our original, we had a total of 3 amps that we had, but now we have dropped our current. We've taken out some of our XC, so we're going more lagging at this point, and we've had an increase in our impedance, which has gone and given us a decrease in the amount of current. From there, we can go and calculate our VA. So we're going to take 2.31 and we're going to multiply that by 120, which gets us to a value of 277.8. So put that one in there. 277.8 VA. And from that VA, we know what our degrees are at, right? 61.2. So this is 277.8 over top of 61.2. We'll punch that in. 277.8 at angle 61.2, which gets me to a value of 277.8 because we're still inside the polar. So now we just go and do that conversion. An X value of 133.8. That's going to have to be my watts. So 133.8 watts. And a Y value of 243. That's going to be my net vars. 243 vars net. Lovely. So we've gone and changed the total amount of XC. We dropped the amount of XC. We ended up going more lagging as a result. There was more XL that was going to be inside of there because my XL went up, my Z went up. Because my Z went up, my current went down. Because my current went down, my VA went down. And if I take a look at where that's all calculating out to become right now, we've got this as my VA. This is my net lagging amount of bars that I have inside of that system. I've got 61.2 degrees. This triangle's not drawn very accurately to 61.2 degrees, but what it's showing us is that we have got we should have a more steep looking triangle. What's my power factor changed to? This is going to be critical to us. 61.2. Cosine of 61.2 tells me that my power factor has gotten way worse. We're now at 48%. Lagging, because we are primarily inductive inside here. If I want to calculate my individual vars that I would have for each of these, the best way to go and do that would be to do my I squared R formula. So I'm going to go and take my I squared, 2.31 squared, multiplied by 30 for this one. And I can take my I squared, 2.31, multiplied by 75.4. When you do that, you're going to come out to a larger value of vars off here, 402-ish. That we're going to end up for this one, vars. And for this one over here, my capacitor, we're going to end up at about 160 vars-ish. If you compare those to our original one, inside of our original one, we had 398 vars. Now we've lost a lot of our capacitive vars. We're down to only 160 vars. If I take a look at my original one as well, I had 679 vars L. And I take a look now, I've got 402. It's less vars L, but the ratio, the proportion of the lagging vars to my capacitive vars has gone up on this one. What we're doing is we're proving the fact that whenever my net XL goes up, and that's really what this thing is trying to go and prove, is that if XL or XC, so we'll just call it XNet increases, then my power factor decreases off of these. This one that we had over here, where we added in the resistance, my example number 9, just showed that when my R increases, we increase the R, we added in that little 10 ohms, we saw that my power factor decreased. Could we take that same statement and flip it around? Absolutely. We could also say that if my R were to decrease, then my power factor would also have to go up. Its value would actually, get worse because we got less resistance. We'd have more reactance that would be inside of that thing. This one over here, we saw that when I had more reactance, I had a power factor that was going down, right, down to 48%. That would also mean that if I were to go and flip that, if my X net were to go and decrease, then my power factor would be going back up. That's the thrust of what they were trying to do inside of these two, was get us to this point where we've gone through calculations. We took an original series circuit, we changed our values, we increased our resistance, and as a result of our increase in resistance over here, I'm actually going to flip these because it's hard to talk about them inverted like that. It's easier to talk about them like this. My resistance goes up, the power factor, like the percent, goes up off of there. It's the phase angle that goes down. When my resistance drops, my power factor goes down. So more resistance equals better power factor. This over here, less X net equals better power factor out of this one over here. All right, that covers us off through that. We've got one more video to do inside of this section. The last section that we're going to go and take a look at is going to be 11, 12, and 13, where we are going to go into series resonant circuit.